Okay, everyone, welcome to the final presentations for the Astrophysical Observations and Techniques course in 2014. The first talk will be given by Yashashree Jadhav. We'll be talking about correlated variations in photometry and spectroscopy for quasars.
Good afternoon, everyone, and thank you, Dr. Feiger, for introducing me. Today I shall be talking about, as Dr. Feiger said, about the correlation between photometry and spectroscopy for quasars. In the background here, we just have an artist's impression of what a quasar looks like, and this is actually one of my favorite illustrations. Just a quick outline of what I should be talking about today, starting up with my motivation and a little background research that I did on this subject, going through my approach and then going through all the steps that I took for the photometry and spectroscopy for quasars and how I compare them. Right, to start up with motivation. So my main science question was that, is there a correlation between the photometry and spectroscopy for time-varying quasars, and is there a model that can compare these two? Currently, there is no model which has a direct correlation between both the photometry and the spectroscopy for quasars. So just a brief review of what I found on the archive was that variability has been observed in absorption lines for quasars, relatively high redshift quasars, and this intrinsic variability was caused due to torus around the quasars. And if you want to read more about it, you can refer to Misawa et al. 2014. So the relevance to my project would be that variability in emission lines for quasars could possibly also be caused due to a similar reason, the torus around the quasar, due to the accretion disk in, as they mentioned in the paper, the lumpiness of the quasar. My approach to answer this problem would be to compare the photometry and spectroscopy of quasars taken at relatively common epochs using both the Catalina real-time sky survey data for photometry and SDSS data for the spectroscopy. Another feature would be to compare the spectra taken for the same object at two different epochs to check if there is presence of variability between them. And the final aim would be to take existing quasar models and see that whatever I can find from my observations can be compared to them to maybe attempt to create a new model which compares the photometry and spectroscopy for quasars. So the first step is, of course, data collection. So this data was collected using SDSS, and what I did was I wrote a small code in SQL to find out all of those spectra for quasars which have at least two spectra, so that I can even compare the two spectra to each other. And these spectra were chosen for those quasars which have both spectroscopy in SDSS as well as photometry in Catalina, so that I have comparison from both photometry and spectroscopy. So the total coverage was found to be about 24 quasars which have, as I said, both spectroscopy and photometry in Catalina and SDSS. And these were chosen to be my main data set. So for the first stage of my analysis, which was the photometry, which is the time series analysis, I found the data for all of these 24 quasars using the Catalina real-time survey. And I analyzed 10 of these, and I'm showing a few of these in my presentation today. So if you want to see more, talk to me later. All of these 10 quasars were checked for variability, as I should be showing on my next plot. So here you can see this is a time series of one of the quasars, and this is magnitude in V band, which is plotted against the date. And you see that there is a distinct variability for the different data points taken at the different dates. So you see that there is a variability going from about 90.6 magnitudes to about 20.6 magnitudes. So that's about a 1 magnitude difference. And the date scale also tells you that the period was in the order of several years. So just to compare another, I'm not sure why that looks like. So just to compare another quasar, we have another quasar which varies on a comparatively smaller magnitude scale. So here the variability goes a little less than 1 magnitude. And to just see how different quasars compare in different magnitude scales, this is one of my less varying quasar series, which you still see that there is a distinct variability in the time series, but this time on about a 0.5 magnitude scale. So, after analyzing all of these 10 quasars, I found that all 10 of them have distinct variability in magnitudes ranging from about 0.5 magnitudes to 2 magnitudes. So this brings me to the second stage of my data process, which is data processing for the spectrum. The first thing that we have to realize about spectra is that these quasars are at relatively high redshift, redshift 1, redshift 2, sometimes even more, which means that all of the lines that I'm observing will be redshifted. So one of the important factors that I have to consider while analyzing my spectra is I have to do a redshift correction, which is basically just correct the redshift which is observed. So say a line is observed at about 4,000 angstroms, but its rest wavelength will be about 1,000 angstrom. So I have to correct it with respect to whatever redshift I get from the data. The second important thing that we have to do for spectrum is emission line masking. So for this, I wrote a small code that went into the spectrum and then chose each of the emission lines so that I can mask it out, and when I fit it, I can fit just the continuum and not the emission lines. This gives a much better fit rather than having the emission lines in and then trying to fit it. This also allows me to have now my emission lines at hand if I need to compare it further, which will be another step that I do later on. The next stage in spectral analysis is polynomial normalization. So as any spectra, all of my spectra would also normalize using an nth order polynomial depending on each particular object. And this allows us to compare the different spectra because say one of the spectrum was taken using instrument A and another was taken using instrument B, then the flux scales will be different. And so I normalize it, then I can relate those two spectra and have a much better understanding of their relation. To help that further, another feature that we use is the spline fit. So say spectrum A was taken from 4,000 angstroms to 6,000 angstroms. Spectrum B was taken from 3,000 angstroms to 7,000 angstroms. So I can't just compare the two because there will be a different correlation between the wavelength ranges. So having a spline fit will make sure that I can compare the spectra in the same scales. And here, in this particular plot, I have the flux plotted against the wavelength. And if you see, there are two colors plotted there. One is the blue and one is the green. So the blue is my original spectrum, and the green is the over-plotted spline fit. Another very useful factor for spectroscopy analysis is smoothing. More often than not, when you get a spectra, there will be a lot of noise in it. So it means that you can't really see your features very well. One very easy way of fixing this is to smooth the spectra, and for my analysis purposes, I use a 5-binning smoothing technique, which is I take the median of 5 bins and use that as my data point. So in this particular plot, I have plotted one example of a spectrum that I had, flux versus wavelength, and in the blue is my original spectrum, which you can see has a lot of noise, and in black is the superimposed smooth spectrum. This not only allows us to get a better understanding of the spectrum, it also accentuates the emission lines so that we can see them more clearly. Now comes the interesting part, searching for features. So searching for features can be done in a couple different ways. First is shown here, which is when I take my two spectra and I compare them to each other, one of the things that I can search for is if there is a lateral shift between the two spectra. So as you can see in this sample case that I have flux versus wavelength again, where I have spectrum 1 in blue and spectrum 2 in green, and you can see that there is a clear shift between the two spectra in terms of wavelength. Another feature while comparing two spectrum is that if you overlay spectrum 1 and spectrum 2, there can be a high difference between the flux in the two. This can be caused by the spectrum being taken at two different dates, and one of them may be in outburst and one is not an outburst. So there will be a much higher flux for one spectrum than the other. And for this, again, I wrote coding in Python to compare the two spectrum and had residual plots to compare the fluxes. So as an example, to see what a normal spectrum looks like compared to another normal spectrum, here I have superimposed in red quasar 1 and in teal quasar 2. And you can see that not only are the fluxes quite related to each other, even when you compare the wavelengths, the two spectra clearly line up with each other, so there isn't any clear shift or any interesting features going on. Now for something more exciting. So in this plot, I have two quasars, one in red, one in teal, and you can see that there is a clear shift in the wavelength for the teal quasar, which is shifted by about 10 angstroms from quasar 1. This can be one of the interesting features that we search for when we try to identify discrepancies between the two spectra. So this can be one of the main identifiers when I compare the two residual spectra. What is it? So while going through these spectra and once I found that one object, suspicion rose in my mind. Is this really so nice? Is this shift really so obvious? So the thing is that SDSS can have some tiny glitches. The main glitch was that for the two quasars, the redshift that was mentioned in SDSS was not the same for both the quasars. For one of the quasars, the redshift was about 1.4. For another one, the redshift was about 1.22. And this means that the emission lines were not masked very properly. So one of the quasars was shifted than the other. One of the reasons why this happened was if you see the second quasar, that was a zoomed in shot of the quasar. So if you would have seen a zoomed out shot of the quasar, there was one line which had a really high noise. That noise could have been recognized as an emission line and should have been recognized as noise, which led to the entire spectrum being shifted. So this is one thing that you have to be careful of when you're doing spectral analysis. Now for some of my spectra of the objects that I showed you before. Another important thing to remember, as I mentioned before about the redshift correction, is that these are the rest wavelengths of the prominent emission lines seen in most of the quasars, most of the time varying quasars that I have been analyzing in my data search. So we see Lyman alpha, helium-2, carbon-4, carbon-3, and magnesium-2 lines at these particular rest wavelengths. For object 2, there were two quasars that I found, the two quasar spectrum that I found in SDSS, which are compared here. This particular data was again taken from SDSS data release 10. And here you see that if you compare the two spectrum, they are very correlated to each other, so there isn't a lot of shift between the two. And I know that the top half of it is somehow gone, but I can tell you that the first spectrum was taken about 5 days after the second spectrum. So these two were taken comparatively close to each other. Here you can see there is a prominent carbon-4 line. There's a helium-2 line which is not so prominent, but there is another prominent carbon-3 line and magnesium-2 line. The number of prominent lines changes from quasar to quasar depending on when they were taken and at what stage they are. Another example is my object number 3. So object number 3 was taken within a day of each other, the two spectrum. And here we see the very nicely prominent Lyman alpha line and carbon-4, carbon-3, and magnesium-2 line. Again, the helium-2 line is not very prominent. There was another spectrum that I found that had not 2, but actually 3 spectrum. So out of these 3, 2 of them were taken from SDSS, and 1 was taken from a new survey, which is called BOSS. So that is, again, a spectroscopic survey of several thousand objects. To compare those 3 lines, I made this plot after smoothing features. And here, the first main prominent line is the Lyman alpha line, and then carbon-4, carbon-3, and in this particular one, the magnesium-2 line is not visible. Now to compare these features, if I overlay a line on top of them, you see that all of the Lyman alpha emission lines line up with each other, which means that there is no clear shift between them. So to summarize, time series analysis of quasars do show that there is a variability in the magnitudes ranging from about 0.5 magnitudes to about 2 magnitudes. The period of these quasars ranges about several years. For the spectral analysis, we see that there is a strong presence of emission lines, in particular Lyman alpha, helium-2, carbon-4, carbon-3, and magnesium-2 lines. And these lines can be used as markers to check for variability between the quasars. One of the things that I wanted to do but could not in this particular case was to compare common epochs. But for the objects that I chose, there weren't any common epochs between the CRTS, which is the Catalina photometry data, and the SDSS spectroscopy data. So that is why I couldn't compare what the magnitudes would be at that particular date. This will be included in my future work. So in the future work that I shall do, I will be comparing the V-band magnitude for the spectrum at the particular epoch that the spectra were taking to see if there is any correlation between the time series. Another comparison can be done with the equivalent widths of the emission line profiles to see if that is varying over time as the spectra is taken. And just to go even further, we can study existing models to find if there is a causal relation between the time series, the photometry, and the spectroscopy of the quasars. References? Thank you.
Okay, and I see we have time for a few questions, or perhaps more. Does anyone have questions? Go back here.
So what do you mean by seeing a shift in the spectral lines?
Seeing the shift in the spectral lines. Okay, so do you want me to go back to my...
Yeah, you can.
So, this one, for instance?
Yes.
Okay, so here, by shift in the spectral lines, if you see emission line 1 and emission line 2 from spectrum 1 and spectrum 2, they are not at the same wavelength, even though this one is redshift corrected. So this means that there was some kind of variability that happened in the quasars. I do not know the cause of that because that is part of my future work research, but which caused the emission line to be shifted by some angstroms. So that is the lateral shift in the spectrum.
Usually it could be due to the gas that is moving.
Right, right. So as I was mentioning before about the absorption lines variability. So they found this due to the fluorescence around the quasar and the gas around the quasar, which causes this kind of a shift. So if I did, so I did not find this in any of the others for good reasons, by which I mean that some reasons that were not caused by discrepancy in the Z values. But if this is occurring, then this would probably be because of the gas around the quasar.
And there's one more. If you go to the figures from SDSS,
Yes?
from the SDS.
Oh, sorry, SDSS. Ah, yes.
Stop.
Yes.
So is that line the magnesium 2 in both the cases that you have plotted, that you have marked?
Magnesium 2? Yeah, the one in the
Shifted.
plain blue, yes.
Yeah, and the carbon is
Yeah.
shifted too.
So do you consider that as a, I don't know, something that is intrinsic to the quasar?
It is, yes.
Is it actually shifted between the two points?
No, that's just because those plots are not normalized for the wavelength.
So it's not shifted.
It's not shifted.
Oh, you said it's not normalized?
The
Oh,
scale
I
of
was
the
saying that the
plots
scale is not the
Oh.
same for both, so that is why.
More questions?
So on those pairs of spectra that you compared, they are of the same quasar but at different moments of time.
Right, yes.
And I think that the only case where you find time difference, this could be due to the redshift discrepancy?
The ones that I found was due to the redshift discrepancy. I haven't found any
So if you
another.
eliminate redshift discrepancy, those spectra would be perfectly aligned.
Yes.
So there will be no actual
Yes.
variability in spectra.
Yes, actually even for this one, the one that I showed here, the one with the redshift discrepancy. So I took the redshift discrepancy out and then they aligned perfectly well.
Well, what are those green and blue lines?
Oh, those were my polynomial normalization fits.
So why do you think that happens, that there is a variability in magnitude but not in spectrum?
So the spectrum variability is probably because the features are the same. So the quasars, especially the time series has been taken over several years, but for the spectrum, the two spectrum have been taken several days apart. So if they've just been taken several days apart, then they wouldn't have enough time to show possible variability. So what we would need would be spectrum taken at multiple years length. So if, say, I take a spectrum today and then 2 years later, then there is more possibility of finding variability between them.
Oh, I see. So the photometric values were separated by like scale a few years?
Yes.
And you just had just two moments of time for spectra
Yes.
separated by
Days.
few days?
Yeah, yeah. For instance, these two that I have, these are 5 days and this is the next day.
So to continue your work, you need to have spectra taken at the same moments of time as the photometry?
Same moments of time
To
as the
find the
photometry
correlation
and
between them?
yes, that and it has to be taken over several years, at least a couple years to see any consistent variability in them.
What is the variability of a typical quasar?
Variability in terms of magnitude, you mean?
Oh, period.
Oh, period. So period can be anywhere between a couple of years to several years.
Is it periodic at all? From your
It's not.
plot, it looks like it's not periodic. I mean, variability in magnitude. The first
In
plot that you
magnitude,
showed us.
so you mean these plots?
Yes, it is. So
These plots,
is that
okay.
actually periodic?
So this is not a full time scale as you can see. So one of the things that I can do in the future is to fit this with a curve and see if it is periodic. But there are several which are not, as you said, it's not completely periodic. You can see that there is probably a period, but it's not periodic.
Yeah, that's what I'm asking
Yes,
for.
yeah.
Is that a part of a period or there is no periodicity at all?
For these, I did not find, but there are quasars that have periodicity.
I have some questions.
Yes.
Let's go back to slide 3, which reminds me, by the way, one of my comments is you should have slide numbers. Yeah. Slide 3. So there's your science question that you asked, and you set out to answer that in this project. So what's the answer? That's a yes or no answer, I think.
So the answer is not very straightforward as yes or no.
So it's not yes or no.
The question may be yes or no, but the answer, as science mostly is not always just yes or no. So the answer that I found throughout my research was that right now there isn't a correlation, but given more data, both photometry and spectroscopy, there can be a correlation between the time series and photometry. The main thing we need is spectra that have been taken over several years.
So maybe the answer here is that I cannot answer this question given the work I've done, but given the future work, I might be able to answer it.
Right.
Is that right? Okay. Let's see. Go to one of the spectra where you've done a polynomial fit to the continuum. Let's take a look at that. Or maybe that one.
This one?
Yeah. Is that what that blue line is? It's a polynomial
Yes.
fit to the continuum. Is that a good fit?
That particular one, so that's to the continuum. So you have to realize that this is after the emission lines were taken out.
So this is like the continuum that you subtract?
Yes,
So is that a good fit?
that was a good fit, yes.
How do you know it's a good fit?
I do not have the plot right now, but once you take the emission lines out as I showed here,
Yeah.
so then you can fit it nicely.
Let's go back to the picture we were looking at. So you think that's a good fit. How do you know that's a good fit? You said something about when you do something, you take emission lines out.
Right, so for emission lines masking, so I should be removing the main peak emission line. So
Can you point to a piece of the continuum in the spectrum in the green?
In the green, yes.
Yeah.
So like this would be the continuum.
We'll just point at one thing.
So this.
So maybe this here is the continuum level,
Mm-hmm.
and the blue curve looks like it's pretty close to that.
Mm-hmm.
And then point at some other ones.
Right. So here goes.
So is the blue line a good fit to that continuum?
No, it's not a good fit for that.
Uh-huh. But over here,
Here and again.
looks pretty good.
Yeah.
When you say, so what routine produced the blue line? Was that something that you wrote? Or was-
Yes.
And what you did was you took out the emission lines?
Mm-hmm.
Did you take out the absorption lines?
I did not take out this.
So the blue line looks like it dips right here.
So
The
that
green line looks like it has a dip.
Mhm.
So is the blue line a representation, a good representation of the continuum?
It's continuum plus the absorption lines.
Okay. So is it better than to remove the absorption lines?
Yes, it would be.
Maybe this one would go up.
Mhm.
This is, looks like this is the continuum. I don't know about
Mhm.
this. This looks like some wings. And in most of the other cases, it looks like there's a significant deviation between the continuum fit and the spectrum.
Mm.
And I'm not sure if that's because you didn't take out absorption lines.
I
Maybe that's.
think so, yeah.
Okay.
So that would be one of my additional future work.
Okay. Go to slide 28.
Okay. 28.
Oh,
think
okay.
I have-
I have, right, go up a slide. I have a previous version. It looks like we added one of
yes.
these lines. Go up one more. Oh, down. Okay, so let's see. What are these lines?
I'm assuming that that's noise
Why do you assume that?
because there weren't any emission lines at those particular wavelengths after rectification.
There weren't any emission lines. When you say there weren't any, in what? Did you look at something?
In the SDSS data. So
in
SDSS.
a catalog?
Yes, yes. So they have, so these particular plots themselves are from the SDSS DR10. So to compare if what I'm getting is consistent with what SDSS is also getting. So they also have a way to plot their emission line, their spectrum with a list of all of the emission lines that they.
Okay, so either it's noise because it's not included in the list, or you've just discovered for the first time in humanity this signature, which looks like it's binary code from alien civilization, and you want to know how much. Or you can just call it noise because it wasn't in some list that someone made. So do you know what this is? Is it when you say it's noise? It kind of looks weird because these variations to me look like noise, right? It looks sort of random. And then this stuff looks like it comes in some certain kind of pattern. But you're not sure what that is?
I'm not sure, but I can look into it.
Yeah. I think the atmosphere is very bad there. That might be poor correction for OH emission. There's also titanium oxide lines there in late-type stars, but I don't know. I don't think that's what that is. It would be interesting to know that. Go back to the slide where there was a mismatch. It looked like the shift, the
Right.
interesting, yeah, right there.
Yes.
Is this shifted back to the rest wavelength?
This is shifted back to the rest wavelength.
Okay, so I think I understand that the observations are done, and the wavelength scale is in the measured reference
Right.
frame. And you shift it back to the rest frame by having an estimate of the redshift.
Right.
And the pipeline, or through some method, there's an estimate of the redshift.
Right.
And it's shifted back. And clearly, the estimate of the redshift was wrong in one of these two
Yes.
cases. How is the redshift estimated?
The redshift was just obtained from SDSS.
How did they estimate that?
So they had the emission lines in their spectra, and they knew what the original rest wavelength should be for that particular emission line.
So do you think that that's the way they did it, or did they use spectrophotometric redshifts, which uses multi-band photometry?
I think that's the one because they do have the multiband data there as well for each of the spectrum.
Because if they were using lines, I would have thought that they would have gotten this right.
Because as I said, for the second one,
Or maybe
there
it
was a
was a-
really large noise.
Oh, okay, so
So
even
that's
using
why.
the lines, it could be a
Yes,
mistake was made. But then you can manually look to see what the shift
definitely.
is.
Yeah, but
Okay.
for this particular case, as I said, it was probably because of the huge big noise that they had for one of the spectrum.
Uh-huh. Okay, if you go back to one of the slides with the photometric variation. Yeah, like that. I think at one point you mentioned something about a torus. And do you think that's related to the photometric variability? Or did you mention it in the context of
In the context of the
spectroscopy?
spectroscopy, yeah.
So what do you think causes this kind of variability?
So this kind of variability would be the intrinsic variability of the quasar.
What does that mean? I don't know what that means.
So that's
Like what's the physics that causes variability? One answer might be, I don't know.
so quasars themselves are high redshift objects, and we know that they it's intrinsic
Let's
variability of the
look
quasars.
at the, if you look at the, let's say you're right here, right?
Right.
And then you draw something having to do with the quasar.
That is quasar.
So what's that thing in the middle?
So that's a supermassive black hole.
Okay. And then what's the other stuff in the little ellipse, the big ellipse?
Big ellipse is everything in that galaxy around it.
Stars.
Stars.
Okay. So we're looking at this system, and I guess we can see a bit of the region around the black hole because it's inclined. You mean it's a bit inclined.
Yes.
Okay, so what's varying here?
So here, what's varying is the magnitude that we observe when we observe this quasar.
Yeah. So what are we observing here? So you measure a certain brightness.
Right.
So it's a point in that picture. The
So
what's
we're
being-
measuring, say, this brightness.
What's in there? I think you said it was a
So-
black hole. Black hole's not bright, it's black. It's
No,
moving.
so this will be all of the light that's emitted from the surround. Yes.
So this is all the stars in the galaxy?
Yes, and it will also be, because it's a quasar at high redshift, so it will also have jets coming out.
So this is the jet?
Does include the
So
jets.
is this, I think you said this is V-band, right?
Yes.
And V-band is sort of around 300 nanometers or something after the show.
About.
So that's kind of like UV. So what is that?
Yes.
What's producing this light?
Um,
Is it a jet, or is it the stars, or is it a black hole? Because I think you've mentioned all
Yes.
three so far.
it's the jet that's producing the.
It's a jet. So what's happening? I guess the jet is making more light.
So it will be dependent on the amount of ejecta from the quasar. So that varies over time.
I thought you were going to say that the clumps in the torus
That would be
are
for the
blocking the
spectroscopy.
central engine, and the central engine is very small, and that these clumps have a sufficient size scale to block or partially block them from our view, and that's what's causing the variation.
So
Is that
they
not-
talked about that in the paper about the absorption lines and broadening of the absorption lines.
But no, but even photometry, what about the photometry, just extincting some of the light from them?
They did talk a little bit about extinction, but in that particular paper, they did not go a lot into it.
So do you know what's causing the variation? It sounds like you're not sure, that it could be a number of things, people have some ideas, but it's not.
Yes, because I couldn't, so as I said, I didn't find one particular model that was relating both of them together, the photometry and the
But I'm
spectroscopy,
just
to
thinking
one
about
particular mechanism.
photometry.
Right, so photometry will be mainly caused due to the jets.
Something's happening in the jet that
Mhm.
changes the variation. Okay, let me see here. that's it. Are there any other questions, maybe follow-up questions?
Yes.
So there are a few measurements taken apparently at the same moment of time, but very different. You see?
Mm.
I mean,
Are you talking
I mean
about?
to the right of 5.40 mark.
So you mean these?
Yes. Well, what is that due to?
Okay, so there are several points in the time series that I saw which were taken at different magnitudes than the rest of the seeming continuum of the curve, if you can say. So what I am not